Thank you, Adib. You didn't have to read the whole thing here. It's a Friday afternoon. I'm really surprised to see so many of you here. It's really a pleasure to get these opportunities to stand in front of a lot of people that you know. Some of you I don't know. So anyway, I would like to thank you all being here on your spending your Friday afternoon here on a technical lecture that is sponsored by Geoscience and Remote Sensing. Some of you, who don't like this time, you can later on see Adib. He's the guy who prepared the timing and stuff like that. So Adib mentioned the title of the lecture, so I'm not going to spend too much time on that. But since this is sponsored by Geoscience and Remote Sensing, I would like to say a few words about this society and what we do in that society. But before I start, I would like those of you who are member of IEEE to raise your hand. So a lot of you are members of IEEE. That's a great society, and it's a very good thing, to continue remaining a member. So very quickly, what is geoscience and remote sensing? We are one of the 38 societies of IEEE. IEEE has 38 different societies and few councils that act. Some of them may become a society later on. We have about 3,800 members. Geoscience and remote sensing has about 300 members. IEEE as a whole has about 450,000 members, and we are spread around 94 countries. So what do we do? Remote sensing and geospatial information is what Remote Sensing Society does, and we cover a wide range of science, engineering, application, and education in this society. And one of the things that when I became a president, we were forced to have a vision was to become a leading society in science, engineering, and applications, and education for remote sensing and geospatial information community. We have also established large number of chapters. Over the past 2 years, we have doubled the number of chapters we have in this society all around the world. And that is going really well. And of course, we have one here that Adib is running. The chapter in Michigan is buried somewhere there among all these chapters that we have in Region 7. And also a number of applications. We do remote sensing of land. This is microwave, optical, hyperspectral. Biomass monitoring is one of the things that is done because of global warming. Monitoring natural hazards, urban studies, planning, electromagnetic theory and application, sensors and platform, remote sensing of atmosphere and ocean, and education and policy. This is what we do. So a little bit of introduction, I thought it would be good. So if some of you are interested to join that society, here is a reason why you can and why you should. So the title of this talk is a little bit, is a subject that I started about 5-6 years ago. I had 2 students who worked on this topic, Jianfeng Wu and Adel Ersherbini. Remote sensing science has been applied extensively, microwave remote sensing, for monitoring different processes of the lands that are on the surface. Why do we use microwave? Microwave can penetrate through atmosphere. You have transmitter and receiver. If it is a radar system on board, it can operate under inclement weather condition, whether it's raining, whether it's cloud or not, whereas optical remote sensing, you cannot get information once you have cloud coverage or day or night condition. So this field has been going on for the past 60, 70 years. And what I would like to do is basically, giving you a brief outline of my presentation. Introduction, this is the quest for energy resources. This is very important. A little bit about radar remote sensing, and then using those techniques that we have developed for other types of remote sensing, see if we can do subsurface sensing. And we started to look at radio wave detection and estimation of subsurface hydraulic fracturing at low frequencies, whether we could use the synthetic aperture radar techniques that we have been using from space, maybe to see kilometers down on the Earth. And then, I'll be talking about some of these SAR images. some antenna work that we have done in order to enable that, and then fracture detection in both bistatic and monostatic mode, and also another application where we are using a dual frequency, this is an airborne system, to allow you to do this type of measurements. So quest for energy, access of course to reliable and sustainable energy is so very important. Energy is what drives the economy. Energy is so very important because of everyday stuff that we do, right? It will influence and shape the future of human society as the number of us on this planet is growing. You know, we all have access to energy, and energy is a source for producing food and stuff like that. So it's very, very important. It's a major factor. If you look back all these maybe 50, 60 years ago, major source of wars and conflicts around the world has been access to the source of energy. So it's very important. You know, how do we get more energy at our disposal as we go forward? And not only we do that, but also we want to make it safe. So environment is very important. The cost of and availability of these are important. And of course, the economy, as I have mentioned. Sources of energy, traditionally we have been using fossil fuel, oil and local, and nuclear, and more recently renewable energy. And you know, there has been quite a bit of investment in recent years in that. You know, of course, petroleum is a major source. We dig the ground, we go kilometers down. There is a recent technology that now we can drill horizontally, so we can have quite a bit of access to a lot of oils that we could not in the past. And of course, coal, you know, this has been a major subject of recent election here, you know, whether we could get access to coal again. You know, there was a lot of regulations on coal that was imposed by this administration. Now they want to relax it. And of course, the issue is the issue of global warming and the effect of that on an environment and so on and so forth. So there are ideas in terms of creating a methodology and technology in order to sequester carbon dioxide. So whatever we release, if we could grab it, not release it into the atmosphere, but sequester it and keep it somewhere, then you could have a zero carbon dioxide footprint even from fossil fuels. So renewable energy, you know, these are environmentally benign technology that would allow you to produce energy with zero carbon footprint. So there has been quite a bit of actually effort into that. You know, according to a United Nations environmental program study that was recently published, the investment around the world on renewable energy, and these are you know, biomass and, you know, wind and stuff like that, it has been exceeded more than $286 billion. This is 6 times more than what was invested in 2004. So this is really catching up. This is an area that it's very interesting to get into. And I'm going to describe some of the techniques that are being considered. One of them that is related to electromagnetics is to capture energy from the sun. Let's say from a sun synchronous orbit. You have a kilometer by a kilometer, you know, solar array, and Steve can tell you about them. And you generate a gigawatt of power. But how do you get that power from a geosynchronous orbit to the Earth? And that is done by microwave relaying that energy at 1 gigahertz. If you have a large antenna, you can illuminate, then you can have a farm on the ground, set up a rectenna, and collect that energy and, you know, produce the energy you want. The issue is, you know, can I have a very large array at L-band in space in order to transfer that energy, and the rectennas on the ground, how do I make the power conversion of those high enough? So this is an area that is being worked. Another very cool idea that recently, this is about, you know, 5 or 6 years, that you create a giant greenhouse. Let me see if I do that. Yeah, it will show it down here. So you have a very large greenhouse. The solar energy comes in here. It heats up this area underneath, and it creates a draft, and you have this huge tower. And that tower pulls all that air out there, and there are turbines around here that could generate energy. And with this, you know, apparently you can generate up to about 400 or 500 megawatts of power. And of course, wind, also ideas of, you know, lifting winds into higher layers of atmosphere where we have continuous flow of current and generate energy there. There are other ideas, for example, creating a Carnot machine from ocean current. So you have a temperature difference between the water above and then the water below. And again, you can create a raft and generate a Carnot machine to do that. And the other one is biomass to alcohol that, again, has been quite successful. When you go to gas station, you can also buy ethanol, or there is a mandate certain percentage of the gas that you use should have methanol in it, and those are all produced by corn, but there are also different techniques for generating that. So radar remote sensing, how can radar remote sensing come into this picture and help? First of all, finding resources of energy, and also once you're doing that, how do we ensure that the energy that we pull out would have minimal impact on the environment? Okay, so radar remote sensing, traditionally we are using that, for example, to get global map of soil moisture. This is a SMAP project. Myself and Liang are part of that mission. This is a NASA radar radiometer technique that we can go and map the soil moisture around the world with a frequency of about three days to generate this map. And why are we interested in this? Because it goes into the global circulation model. We can predict weather better and all of that. Biomass, it's very important. There is sink of carbon dioxide, and there is sources of carbon dioxide. We are sources of carbon dioxide through our industrial operations, driving our cars. What is the sink of carbon dioxide? Is the vegetation, right? Vegetation through photosynthesis takes in all the carbon dioxide from the atmosphere and can generate a balance. Also, ocean has that capability to do that. So we have been actually involved. My PhD thesis was on this about 30-some years ago. We started looking, what radar can do in order to measure biomass around the globe, in a quantitative manner. So we have developed a lot of models. We ran a lot of experiments to do that. We can do ocean winds, we can do ice and snow, we can do crops, and then we can also estimate natural hazards. All of these are sort of for targets that are on the skin of the planet. We cannot go deep inside because electromagnetic wave cannot penetrate, especially from space. If you are operating in a space and you want to radiate 1 megahertz, ionosphere would stop you. Ionosphere would reflect all that energy because you have a sheet of basically a metallic or a plasmonic surface on the surface of the planet that doesn't allow the signal to go through. So we wanted to look at that, and one of the problems that I thought was very important about 5 years ago was just when people started accessing a lot of gas and oil resources through a technology that has been recently developed known as fracking. So fracking basically, you drill the ground, this is 1 mile or more. You can go down and then you can go horizontally into the ground. You go through the shale rock. Shale rock has been known for many, many years to the geologists that they contain a lot of gas and oil that have been there for millions of years. But we could not easily extract those because they are trapped, right, in the shell. So what they do, they pump tremendous amount of pressure. This is water that comes in here, and then you have more pumps here, and you would create tremendous amount of pressure in order to crack the rocks and create these cracks into the rocks to release the trapped gas and oil. And then it would percolate down to your field after you have done the fracking. Actually, they also put some chemical in that water, and they put something that is called propens. It's similar to a very small sand particles that once you crack, the sand particles would go through the crack, and then when the pressure is relieved, sand keeps the cracks open, for example, right? So there is quite a bit of technology just to do that, and a lot of these things are all classified, and people don't know what sort of chemical is mixed in order to make the water not compressible and maintain that type of pressure so you can do cracking, for example, down there. So what are the problems with this? So before I get to the problem, let me just give you some data information. This shows, the US shale gas production from 2008 to 2015. And you can see, almost an exponential growth here because of this technology, right? And look at the price of gas in US is going down. Every other country, for example, especially those that are using, in Japan, for example, that they don't have access to, the price is going up, it's inflation related, but in US has gone down. The reason again is the fact that we have access to this technology nowadays. So I have already talked to you a little bit about, how do we do that and get access to these gas and oil, but there are also issues and problems related to this. The problem is that once you have these pressurized gas, there are some natural cracks on the ground. There are also, the pressure can also crack the rocks and open, big cracks. And then this chemical that you're pumping from here, and these are all nasty chemicals that you're pumping down, can percolate down to aquifers. And these aquifers are basically eventually through the municipal wells and things like that gets distributed. And you start drinking that water, and then you get sick. A lot of people in Midwest, for example, certain areas, they were getting sick for many years and they didn't know why until somebody related that sickness to the chemicals that exist in fracking, so there have been demonstrations that they don't want to, we don't want to drink, money, even though this creates job. When it comes to your drinking water, you don't want to, further continue on that. So what is a safe way of monitoring how far this fracking takes place? It would be very nice if I could map, once I drill the ground, if I could map the extent of this fracking area. How do we do that? So the current technology doesn't have any techniques like that. If you want to do any type of measurement, you have to attach sensors to your drill bit, send it down there, and then try to monitor. But since you have a lot of water and you have a lot of chemicals, conductivity is very high here, and you don't get much penetration. So any measurement that has been done, it's very close to the horizontal well and nothing beyond that. So there was a need for this, and we started to look into that, and we say, okay, we know the conductivity of this material, combination of water, mud, and sand and rocks. We can estimate the dielectric constant and propagation of the signal at microwave frequency, for example, and find out how much is the penetration through that. If you want to have kilometers of propagation, you have to go very low in frequency. The reason is your wavelength is very long. If your wavelength is very long, then attenuation is a fraction of wavelengths all the time, right? So if you go to lower frequency, since your wavelength is very long, then you have the ability in order to penetrate more. So you go to the desired band of frequency actually is in this MF band, where wavelength is quite long. At 3 megahertz, the wavelength is about 100 meters, and this is about a kilometer at the lower end, and you would get quite a bit of penetration distance. But then the size of antennas that you have to use, which is going to be lambda over 2 or comparable to that, also becomes very large. How do I put an antenna this big underground in order to do mapping? And how do I get resolution from an antenna like that? Because the fracking regions that I want to measure the extent are on the order of tens of meters. How do I get tens of meter type resolution with a system like that? These were a bunch of questions that we wanted to do. So very early on, we started to see if I can design an antenna that could operate in an environment like that, then I have a hope of doing radar imaging, right? So we started looking at these borehole antenna at MF frequency. We started to look at these type of dipole antennas that are folded dipole antennas. And if you have half a wavelength, basically length of that, you could get this to go to resonance. But we also get that antenna and we wrap it around a high mu material, a ferrite core, and in a nonlinear fashion, and I will tell you later on why we need to do that on nonlinear fashion, basically in order so that when you open this up, you get that lambda over 2, But when you wound it, you would get something that is only close to 21 meter type, and you can insert that into the ground. So you can design an antenna like this. It will give you a poor radiation impedance, it gives you a poor radiation efficiency, and it gives you a very narrow bandwidth. So we can make the antenna, it becomes very narrow band, it has a poor radiation, but the good thing is that I don't have much of a signal to noise problem because clutter down there is very low. Interference down there is very low. There is absolutely no signal down. So there are some advantages operating underground, but you know the disadvantages, as I mentioned, are the type of antennas that you have to design. You would do that multi-core, and then you can further reduce the size of these antenna, and you can create basically an antenna. Then we have to also feed this antenna by a cable, and that's why again we are using these ferrite cores, because if I put a cable that goes through my antenna, that cable, which is perfect conductor, is going to short circuit the antenna. An antenna would not radiate unless I have that ferrite core inserted in between. Anyway, so you design this antenna, you operate it, you know this antenna is going to work, and you say, okay, if I now have a kilometer deep hole, if I send this antenna step by step down, and at each location I measure the amplitude and phase of whatever I see. If it is a transmitter and receiver signal in a monostatic way, I can do a synthetic aperture, which means basically you have antenna at different locations as you lowering it down. Let's say if you have another receiver for borehole, you have another antenna here. For each location of the transmit, you move the transmitter antenna along these paths, and then you measure the amplitude and phase of that. And later on, you can do post-processing in order to do beamforming, right? Another thing that you have to do in a configuration like this is that if I have a transmitter antenna and if I have a receiver antenna, let's say this is the fracking region, the characteristic of this fracking region is going to be quite different than its environment. The conductivity of the ground near the fracking area has increased by many orders of magnitude, and therefore it's quite different. It's like a perfect conductor buried underground, and you can measure that. So an important issue is basically to create a null between transmitter and receiver. So what you do as you move the antenna, let's say in steps, you would analyze the antenna in pairs so that a pair of antenna at two locations would always create a null in the direction of the receive antenna. So you can process basically your synthetic aperture signal processing in a way that combination of every two antenna that would create a null in that specific direction where your receiver is. And that way you can create basically 50, 60 dB more isolation between transmitter and receiver. And then when you are doing your imaging, you can basically create an imaging that would allow you to do that. For example, this is when you do a focusing of your array over the region. These are the side lobes, and this was for a condition, for example, where the receiver was in this location where you have not only are focusing your beam over the area of the target, and of course you can move this beam along here. One thing that you know is the horizontal direction of your borehole, horizontal borehole, because that is already known. You drilled in that direction, and you know where your receiver borehole is. So while you are focusing here, you can always also at the same time create a null in the desired direction. You have enough freedom to do that, and that would allow you to do imaging. So basically, you can have a simple model. The simple model, the first thing that you would do, you say, okay, this area is a homogeneous area. You can find, for example, the effective conductivity of that medium, and then you would put that into a model, and now you would get the conductivity. Since even though the conductivity is relatively low, at these low frequencies, this acts almost like a perfect conductor. The reflectivity of this surface is tremendous, and you can actually see that material by putting a transmit array and a receive array and then do a beam forming on here, you can create images like that. So for example, you can just look at the biostatic scattered field from that. You know, if this is a homogeneous region, you have a forward scattering that is very strong, and you also have a specular reflection that is very strong. This is the incident field, and this is the total field. And you process basically this received field in the horizontal array in order, again, to focus it for all receiver location on this in order to map this area. And this is basically in the XZ plane map, where you can see, you can very nicely focus on the region. This allows you to also find out the extent of that. But since I only have one horizontal transmit and receive plane, in XY plane, in this plane, in the horizontal plane, I don't have much resolution. But as I mentioned, I really don't need to have a resolution there because I already know where my whole horizontal borehole is. In order to enhance the lateral resolution, of course, you can use other boreholes. But you know, this is not very practical because drilling these holes, each is going to cost you about $300,000-$400,000. People don't want to do that. And even drilling a second hole is very difficult. You know, we were collaborating with Aramco in Saudi Arabia, and they were telling us, you know, drilling these holes is really expensive, and whether we could do this in a monostatic as opposed to biostatic mode. The reason we were doing this biostatic mode, if you remember, my antenna was very narrow bandwidth. I could only transmit a single frequency through the antenna. And you know, I needed to have a distributed array in order to do my basically beamforming. In a monostatic case, of course, you have to make the antenna wider band. So you know, this is the result. If you have multiple horizontal borehole, now you also get quite a bit of good resolution in XY plane, and you can map the extent in the horizontal plane. So that was a homogeneous case. You know, you can also go and create basically a better model for the fracking region. And in that region, you know, you model all these cracks in terms of impedance surfaces, and then you have an irregular shape. This is more characteristics of the type of fracking, and radar backscatter becomes more pronounced, and you can easily see the fracking region. You don't only have, let's say, this specular point if you consider that as a cylindrical, for example, object. So now, since this is irregular, you get a scattering from all directions, and now you can map this from that. So let's go and take a look at, you know, what can you do in a single hole imaging technique, where now you have a transmit antenna and you have a receive antenna cascaded. These are dipoles in a single hole. You transmit from the transmitter, you receive from the receiver, and you have a little bit of separation between them so that you would minimize the crosstalk between transmitter and receiver. Since you're doing dipoles, you know, radiation of the dipole along the axis of the dipole is minimum, but nevertheless there is some coupling there. And then in order to increase that, the only way you can do that is to increase the separation between them. Okay, so the question was, if you're going, since we are using very low frequencies, the separation between the two antennas, he was asking, Tony was asking, how much are the separations so that the near field coupling between the two antennae is minimized? If we choose a separation of λ/2, as I mentioned, then you can really get rid of that. So here is actually, you know, the isolation you get between these two antennae, Tony. Simulated separation of 30 meters, 70 meters, and 100 meters. You can get 50, 60 dB of isolation between two dipoles that are coaxial. And then if I had bandwidth, if I could operate the antenna in a step frequency mode, then I could also use time domain gating. So one of the things that is very neat about this antenna is that the matching network that you have, which is a transformer to match a 50 ohm into a 2 ohm impedance, if you put just a capacitor, a varactor there, then you can also tune the resonant frequency. So you can go, for example, from 2.8485 all the way to 2.95 or 3 megahertz. that is going to give us enough bandwidth so that we can do range gating. If I operate the radar system in a step frequency mode, so I tune my antenna at a given frequency, I radiate the power I want, I get my backscatter, then I tune my frequency, and I repeat that over all these frequency steps, and as a result, I can again synthesize a very, not a very, but a narrow pulse. And then that will give me range resolution, and that's how you can basically separate, the leakage that is direct between the transmit and receive antenna, let's say from a target that is at a distance of 1 kilometer away.
What sort of power densities are you talking about?
So the power that you would require, for example, in this type of operation are hundreds of watts. So you don't need megawatts or kilowatts. You have enough sensitivity to do that. The attenuation that we are expecting to see from this type of propagation is only under of 20, 30 dBs. Because you're only moving, 10 wavelengths, 15 wavelengths from the target. So fortunately, we don't need megawatts of power in order to get to the signal that we want to get. Hundreds of watts to a kilowatt is sufficient to do. And we did a simulation. Basically, if you bury a metallic sphere, you have now a synthetic aperture that is your cross-range resolution, and you're doing range resolution using frequency by a step frequency technique. And you can have a mapping underground of, let's say, a metallic sphere in this case. Or if you use, for example, a fracking model that has an extent of 400 meters by 300 meters by 250 meters, this is the type of image that you would get, and that would allow you to do the extent of the fracking. So for example, the pipe, the horizontal pipe is here. This is how far, the fracking extent is, and it would show up very nicely, and how far this goes. And this would allow you to not only utilize the region well, because if you didn't frack enough, you want to increase the pressure to extend this, but at the same time, you don't want to pressure too much so that this would extend all the way to the top. So, that becomes a technique to monitor and design that. So, by the time we finished this, the price of oil went down. The price of gas went down. Everybody who was doing fracking stopped, and our project stopped. So we were supposed to go and do field experiments on these. We were expecting, a $5 million project from Aramco that didn't arrive. Okay, I'm looking at the price of oil every day, hoping that this price eventually goes up, and then I can start showing what I did. But we wait. I'm sure it's going to come. Okay, so we are putting this in a box for now until the price of oil again goes to $100 a barrel. Then we come back to this technology.
When are you retired?
So he's predicting that would never happen. Okay. Along the same way, we were doing another type of measurement. This was also a project that was funded, by Saudi Arabia. At the time, they were doing a lot of seismic measurements. Okay, and if you look at the map in Saudi Arabia, there is the biggest reserve is in the empty quarter, where there is quite a bit of sand. And these sand dunes have been created over hundreds of thousands to 1 million years. I don't know how long. But these are huge. And what is worse for seismic wave propagation than loose sand? Nothing, right? Because as soon as you put a seismic, let's say detonation, if it is on a sand, since sand moves, your signal attenuates and doesn't couple to the ground easily, and your signal is done. So they wanted to know, where do they have to go and start doing these seismic measurements? Of course, areas where the sand thickness was the least, right? So how could you map an entire subcontinent of Saudi Arabia, that big area, and measure the thickness of the sand all over the place? And you have to do this every so often, because the sand dunes, as you know, they migrate. So if I created a map, if geologists went there, do this, this is very costly. So it would be nice if you could generate that map of sand layer thickness and provide this using a remote sensing tool, an aircraft system, or better, a space system. Okay, so we wanted to develop a remote sensing tool. I have already explained why we wanted to do that. You have a sand layer usually over a bedrock. And you want to measure this thickness, both horizontally, and generate basically a sand height map. This is again, that explanation of, you put an explosive charge, you explode these, shock waves would go through, and then as it goes through different geological layers of the ground, you get reflection, and then you have these geophones that receives from the delay, you measure basically the mapping. It's like a GPR, it's ground penetrating radar, but in an acoustic or seismic way. So you want to do this type of experiments, for example, in an area like that where attenuation is low. So people have been trying to do this using ground penetrating radar, but this type of measurement is very costly. It doesn't provide you an extended area. It's only one-dimensional, and it's not very accurate. Actually, if you were to do an area of 100 kilometer by 100 kilometer, it would take you a lot of time. Even if you mounted, let's say, on a vehicle, these type of GPRs, and then you had so many vehicles that simultaneously could move around, it would take you 6 days, almost 7 days. If you put it on a helicopter and then try to run that, that would take you about 2 days. But if you had a synthetic aperture radar, I could do this in a very fast, maybe 10, 15 minutes, and then I would be finishing. There are different techniques, for example, currently, to get the height variation, not subsurface, but height variation. And there are techniques based on LiDAR. You get very high resolution, but the cost is very high. You can go, a stereo SAR. You can go interferometric SAR. You can go with optical system stereo. But then you have different resolution and cost. We want to bring basically the resolution high and the cost low for this operation. So synthetic aperture radar, I have already told you, for some of you who don't know, basically in order to get a very fine cross-range resolution, you put a wideband antenna, a wide beam antenna on the side of a radar, on the side of an aircraft, and have the aircraft fly, and then you measure the backscatter amplitude and phase at every location, and you do a post-processing basically to create a very long synthetic aperture, and then processing that would give you a very fine cross-range resolution. So what is interferometric SAR? With interferometric SAR, if I flew the radar in two parallel paths so that there is a difference baseline between the transmit and receive antenna, or this could be transmit and receive, this could be transmit or receive, or this could be transmit, receive, this could be only receive. This is called single pass versus repeat pass interferometry. The signal that would come down, it goes here and it goes there. From the difference in the phase of these two, and knowing basically this baseline distance and the baseline angle, I can measure the height. So we can measure the height using the phase of backscatter measured by two antennas. These are the two aircraft. Let's say this is a repeat pass. You get a SAR image 1, you get a SAR image 2. You have to co-register these two, so you need ground control points. And then you co-register the two images. You look at the phase difference. Once you have the phase difference, you would get an interferogram phase. So you would get phases that are like this. This is the phase difference. Now you have to do, what you have to do is to unwrap the phase, because phase is modulus 2 pi, right? And you do that based on some a priori knowledge of the area, and then you wrap this. Now you have, let's say, an increasing phase and a decreasing phase, and you relate that increasing and decreasing phase to the height or topography of the surface that you are doing the measurement, and you would get, for example, unwrapped interferogram phase that is proportional to the height of, let's say, the scene that you are seeing. Okay? That is a conventional interferometric system that works if you are going to measure the topography of something that is exposed. But we want to do two things. We want to do topography of the sand layer, and we want to do the topography of the bedrock that is buried under the sand. So again, you need to understand the wave propagation. Sand, fortunately, is very dry in these regions. It doesn't have moisture. If it doesn't have moisture, it means that it doesn't attenuate electromagnetic waves much, right? So if my wavelength, again, is long enough that the wavelength is many, many times larger than the smallest particles. Sand particles, at most are 1 millimeter or so, right? So if I had a wavelength that is, let's say, a meter or so, it wouldn't see the sand as a heterogeneous medium. It would see the sand as a homogeneous medium, and you would not get what we call volume scattering. And if you don't have volume scattering, and if there is no moisture, the signal goes way down, and it sees the interface between the sand and bedrock that have a different dielectric, and it would scatter from that and come back up. All right? So here is the idea. We want to use two-frequency interferometric SAR system. One is at very high frequency, Ka band, 35 gigahertz. Why do I want 35 gigahertz? Because now I want a scattering from the surface of a sand. Sand actually is very smooth, so I have to rely on volume scattering. Sand particles, as I mentioned, are millimeter size. I have to use a millimeter wave radar. That's why Ka band, right? And that would give me volume scattering, and I would get a scattering from the top of the sand. That signal does not penetrate into the ground at Ka band. However, if I use a VHF SAR, that VHF signal would penetrate through the sand. It would go through the layer, sees the bedrock, and it would get a scattering. And actually something interesting happens. This surface doesn't even have to be very rough in order to get scattering from that. The reason is refraction. Refraction of the signal of, let's say, VHF signal. As it reaches this, it bends and it comes almost normal down, and you will get significant backscatter from that. So I have already mentioned, why do we want to use these two techniques? Why we want to have roughnesses here that are only maybe few centimeters. We still want to use it because of refraction. And I would show that the high frequency, as I mentioned, comes from the top. Then it doesn't, not much would penetrate because you have volume scattering. Ka band doesn't go down. And then we want to go to low frequency illumination, where we have negligible backscattering from the surface, because surface is smooth, and that is good. And then penetration is very high, and I would go and it refracts. As it refracts, it almost goes normal incidence to the surface, and I get quite a bit of backscatter. So there are two key important factors here: low attenuation, refraction, and normal incidence to the surface, almost. That would give me quite a bit of backscatter. So now I can generate interferometric SAR at low frequency. Okay, so this is again the same standard technique. How you would do that. You would go there, you have this interferogram phase that comes from the lower layer, but there are quite a bit of issues here. This is an area that has not been studied before. How do I perform subsurface InSAR processing? And few things are happening here that is not common. One, we have to do image co-registration and phase unwrapping that is similar to the conventional. And then the most important issue is that how do I perform subsurface SAR focusing and height estimation? So we did a simulation, for example, if I had a sloping bedrock and if I had a sand dune, linear sand dunes like that, if I didn't care about the fact that there are sand dunes and there are topography on top of it, and if I ignore refraction and all of that, the interferometric SAR at VHF would produce this result for me, which is really off. So even if I had the height of this and I subtracted that from that, I would get wrong results. So I have to account for the fact that signal would refract. I have to use the topography because that topography of the top surface affects the height and all of these. So in order to do that, you have the Ka band SAR, gets me the top topography. So if I run the Ka band SAR, the nice thing is that now I have the topography of the top surface. That is input to the second step, which is doing topography of the subsurface. I use that information in order to do that. So now I have this topography. My SAR measures this phase difference from which I can find this delta R, and then I have to focus them at a point on the ground. I don't know how to do that because I don't know this height, I don't know how the signal comes in, and so it's a big unknown. And what we did, we came up with this iterative algorithm in order to catch this bedrock height, because the speed of electromagnetic wave into the sand is different than air. Because of that refraction, the location that it hits, all of that is unknown. Basically, interferometric SAR, what it does, it measures the angle of incidence within a thousandth of a fraction of a degree. That's how you know where your target is, where the height of that target is, because you can measure that incidence angle so very accurately. The range information is given by, the delay, but this is basically what, from that phase difference, you can extract. So basically, if you have the phase difference, you have the baseline distance. If you invert this equation, that gives you the incidence angle very, very accurately. All right? So I'm going to assume that initially I would extract this based on the error phase measurement, and I would get this angle. I have the delay. That would give me a location here if I didn't account for the refraction, right? Since I know the height of the surface from the Ka band system, I would estimate the height is this much. I start from that. So I say, okay, here is my height. And then I also find the slope here. And then based on this height and a slope, I think the refraction is taking place here. Because now I can come along that path. I have the slope and I have the height. Then I would refract the ray and I would come here. So now this path length, electrical delay, plus that electrical delay corresponds to that range. Then I say, okay, maybe now the answer is this. All right, then I would iterate for the next round, because now I would, based on this height, I would go and estimate a new incidence angle. And that new incidence angle is going to give me a new estimated height and slope at that point. And through this multiple iteration, I would get a better and better location of the ground. So it's an iterative process. It's somewhat computationally extensive, Eric. So if you can help here. To do this, for example, that would help us to generate these maps quite rapidly and then get to the height. And every time, so when do I converge? When the estimation of the sand depth between two iterations is below certain value, then I stop and I know, for example, I have reached that value. So if you have, for example, planar sand and planar bedrock and sloped sand, this shows you how fast these iterations. So if you use conventional, that you would get a wrong height. First iteration, third iteration, after third or fifth, you would get to that. We did that over multiple cases. Always after fifth iteration, we always get to the correct bedrock. And this technique works quite well. In order to test that, we developed a scale model in the lab, because again, running these aircrafts and making these synthetic aperture radars would require hundreds of millions of dollars. I don't have that, but what I have, I know that electromagnetic wave scales with wavelengths. So I can, if I am a VHF 100 megahertz, if I go to X-band, that's a factor of 100, I can shrink everything. So we did that in a lab. We have an XY table. We put an XY, basically an antenna on the XY table. We ran that. That's my synthetic aperture radar that generated. This is an actual image of this sandbox that I have here. I have a bunch of corner reflectors on top that are observed. This is scattering from a rough surface we have under the sandbox. So this is the radar image with extremely high resolution. This is about 3 or 4 millimeter resolution on the ground that you see, but you scale that, that would be basically a Ka band. This is now the second flight, and that would give me a second image. I have to co-register these two images in order to get the phase. So we can actually find the height of the surface very well. We can, all these corner reflectors are given correct height. If you do basically the measurement of the bed without basically using the algorithm, you get this error depth. But if you apply the algorithm I just gave you, it will give you a very correct height of the rough surface underneath for this estimation. So then there are other types of distortions. For example, you have, if you want to do cross-range, if you want to get the actual geometry, if you want to co-register, let's say if you were looking for archaeological artifacts under sand, you wanted it to map underneath, right? And you have to basically go and correct for the geometrical distortion. Let me show you. So if you have, let's say, a geometry like that, if you fly an aircraft, you would get cross-range resolution distortion. Actually, this image would be mapped like that. So you see that instead of getting a uniform array, these are displaced. You cannot focus them all correctly. And again, we went through an algorithm that would allow you to also correct for that. You have to do this back projection, keep track of that, go through an iterative technique. Again, I don't want to take a lot of your time here to drag you through this math, but that's what you can do in order to basically do this imaging. What you do is that you do a processing where you analyze a portion of your flight where you have a poor cross-range resolution. You get an estimation, and then through an iterative process, since you know the top topography, you can correct for that, and I'll just show you some results. So again, that is a Barchan Dune, where you have a topography also underneath. If you don't do this geometric correction, you can basically measure the depth of this correctly, but then the array is distorted. But if you go through this algorithm I mentioned, you can retrieve exactly the location of these, and to the extent you can also focus them, it will give you the information that you want. So I think there are a lot of more details that I skipped here in the, I guess, benefit of the time that it is already 6:30. You have been sitting here for 1 hour. I better stop here and ask you if you have any question.
It hasn't been easy.
Whoa!
The robot falls, it breaks.